dropout. Learning rate, they have said that initialize for something and they keep on reducing it. So exponential decay is anyways going to be there in your learning rate. And they have done 7 CNN ensemble. So you can have multiple CNNs, and then at the decision that so you can combine multiple CNN at feature level as well as at decision level. So feature level means that the last layer feature over which you are going to apply the classifier, you can merge all of them, and then you have a bigger feature vector for the last layer, and then you take it to your final classification layer itself. Or you let each and every neural network give you the decision, and you can do ensembling or fusion at decision level. So if you see that this was AlexNet, it was 11 by 11 first layer, and then now the point is that ZFnet in 13 comes. ZFnet is nothing. Instead of this 11 by 11 and 4, they have said that I am going to apply 7 by 7 filter. That's the main difference. From that 11 by 11, they have come up with 7 by 7. And with a stride of this equal to 2. And the other thing is that the con 3, 4 and 5 were instead of this and this filter. So they were having less filters, they are having more and more filters. So now you see that it is having more and more parameters. So it's essentially that ZFnet come up with a deeper or one can say the similar, exactly similar network, same number of layers, but actually more and more parameters. It performed very well. I mean, very well, like performed better than the AlexNet at that point of time. But it came in the next year. At that point of time, if I show you, if you have seen, you may wonder that there are actually two things being shown. Something here, something there, something here, something there. Actually, it was not possible for them at that time, 2012, to implement this AlexNet as a single thing. So they divided it into two parts. Part 1 is running in GPU 1, part 2 is running in GPU 2, and then whatever you are getting after each layer, it is going to be merged and combined after each layer. So you can see that things from there coming here, things are here, they are going there. So at that point of time, they were not having a big GPU, so because of that, even this simple AlexNet, they have divided into two parts and somehow shared these things here and there so as to get the. So here you can also see that 4096, it is actually 2048 and 2048 like this. And then comes, so this was the main difference for them. They have got a more and more set of weights. Now comes the VGG Net. VGG Net is a very, very elegant and a very good network. Here you see that what the good thing is that it's completely symmetric network. And this is actually coming from the Jason Mann's group. They were having expertise in computer vision. So now after this Alex and ZFnet, Jason Mann's computer vision group, those persons who used to work extensively on computer vision, they came and want to solve this problem using this network. They come up with a very, very elegant and the simple network. The very simple part is that each and every layer, only 3 by 3 convolution. Very symmetric network, 3 by 3, 3 by 3, 3 by 3, everywhere 3 by 3. First layer, maybe 64 such things, 128, 256, 512, 512. And after that, continuously you are having max pool, max pool, max pool. Very easy, straightforward and simple, intuitive network. It performs very, very well. Even you take this network and apply it over any type of classification problem, decent enough results you are going to get. This is the parametric analysis in which you can check that most of the time for each and every place they have written that how many number of parameters. You will see that these are the number of parameters most of the time. But as soon as you apply first FC, these many number of parameters. So because of that, most of the weights are actually coming from here. If you take this and add whatever you want, it is being dominated by this number. First FC. Now, very small thing about this dropout that I want to tell. In 2 to 3 minutes, we can easily understand how this dropout works. and what is the reason behind this dropout. Okay, so this dropout essentially says that I have a network like this and you have other nodes which are coming like this. This is okay, and things are fully connected. Now what we want is that, as you, some of you may be knowing, that while I am taking this and passing my input inside me, this is my input which is coming, and I will say that for this layer and this layer, I am randomly dropping few of the nodes. Few nodes are actually being dropped. What does it mean? If I drop few nodes, my network becomes different than the previous network. First thing. Second, it becomes less complicated than the previous one, and only these are going to contribute since it is connected to everything. So everything is connected to everything. Network is essentially the same, but how it's being done is that for every layer I randomly choose a vector which will actually be a 0 or 1 for each and every neuron. Which means that what are the things that I wanted to exclude randomly. For each and every sample batch, I will take this batch, I will choose for a layer, I will just not be using few neurons for my forward pass. What will happen is that every time a network is being trained and every time few of the neurons are not going to be used at all. By this, what is going to happen? You will actually be having a less constrained network for each, even though you are having more and more neurons, few of them are actually not being used. So how it is going to work, because our time is over, so maybe in next lecture slightly more details about this dropout